Stephen has received his BS in mathematical physics from the State University of New York at Buffalo. His career has been focused in test and measurement industry and has previously worked for Agilent Technologies and now is a field applications engineering manager for Teledyne LeCroy, where he specializes in signal integrity and high-speed serial data analysis testing solutions. We all appreciate you joining us. We know how valuable your time is. Steve, I am now going to turn the presentation over to you.
Thanks, Hillary. Thanks, everyone, for joining us today for discussion of S parameters and some of the insights we can learn from looking at S parameters. So I'm going to start off by giving some background information about S parameters and what they are and how we can measure them. And then I'm going to go into some more detail about some of the patterns and things that we can recognize in the S parameters and what they can tell us about our interconnects and what kind of insights we can gain from that. So first of all, what is an S parameter? Basically, it's a way to characterize some interconnect. So here's a picture of just some PCB, but we can imagine if we want to be able to tell everything we can about that interconnect, we can send some precision reference signals into it, and we can look at how they scatter off. So we send in some incident wave, and we can look at what reflects back and what transmits through. And by doing this, we can completely characterize the interconnect, and we can know everything that we want to about how it's going to affect signals traveling through it. So we can do this in the time domain, and this is called TDR, or time domain reflectometry. So in that case, we send in some fast rising edge as the incident wave. Some part of that is reflected back, and that's called the time domain reflected, or TDR wave. And some of it gets transmitted through, so that's the TDT, or time domain transmitted wave. So if you think about that fast step, that's basically comprised of a number of different frequencies, right? So there's some broad spectral content to create that fast edge. And so you can decompose that into its various sine wave components. So it's identical to talk about this in the frequency domain as it is to talk about it in this time domain. So in the frequency domain, we call the reflected wave, we call this S11, or sometimes the return loss, and the transmitted S21, or insertion loss. And whether we measure these things in the time domain or the frequency domain, the information that's contained in that measurement is identical. So we can measure it in the time domain and convert to the frequency domain, or we can measure in the frequency and convert to the time. And so up here in this image is showing just a comparison of measurements that were done in the time versus frequency domain, and then displaying them in different ways. So no matter how you look at the information, it's identical. It's all contained in either domain you want to look at. It's just helpful depending on what you're searching for and what you want to understand about the interconnect. Sometimes it's more helpful to look at it one way versus another. So when we're talking about the frequency domain, we're typically talking about S parameters. And what the S parameter looks at is it's a ratio of the waveform out from one of the ports relative to the waveform into a port. So on this side, we call it S11, which is the reflected wave over the incident wave, and S21 is on the output, which is the transmitted over the incident. So we can get S parameters from a variety of sources. I'm showing here the Teledyne LeCroy Spark network analyzer. This will measure S parameters from DC to 40 gigahertz from anywhere from 4 ports or 2 ports up to 12 ports. You can also simulate S parameters, so you can there's different circuit simulation software out there, Quicks and some other software packages. And there's electromagnetic simulations, 2D and 3D field solvers. So you can use a variety of different tools, either direct measurements or simulations, to measure to actually get the S parameters for some interconnect. And we can get the same information out of the S parameters regardless of how you measure them. Actually, something else I'd like to mention in this slide. Typically, we're going to measure S parameters as single-ended S parameters, and you can convert using math between single-ended and mixed-mode S parameters. So usually, it's easier to measure them single-ended and then do the conversion in math rather than trying to actually measure a differential S parameter. So here's an example of a device, some interconnect microstrip trace we have up here. And you can see there's an end to this trace that we're going to call a port. And the port is basically the interface between the measurement and the interconnect. So that's how we're actually going to connect to the device to measure it. And the port has two connectors on it, or two conductors, I should say. So there's the signal path, and there's a signal return or a ground path there as well. And that's going to be true for every port. And then on the left-hand side here, we have actually our network analyzer, which also has a port on it. That has a precision 50 ohm impedance port, and this is going to act as our signal source and also going to measure the reflected signal. So we can send some waveform out of our network analyzer port into our device under test, this trace, and we can look at what gets reflected back coming out of it. And so that's going to depend on the impedance that's seen going in there. Remember, the network analyzer port is 50 ohms, so if there's any variations from 50 ohms in this trace, we'll see some energy reflected back out of that port. It's also going to be really important to understand what the termination on the other side of this trace is. So that's going to play a big factor in terms of what gets reflected back. And that's important in understanding the S parameters and what they mean. So with a one-port device like we have here, we can measure S11, or return loss, which is going to be that reflected wave versus the incident divided by the incident wave. And if you look at what that would look like here, you can see there's an amplitude and there's a phase for each of these waveforms. So this is going to be a complex number that we can describe with real and imaginary parts. Typically, people look at the magnitude, and that's usually the more useful of the magnitude and the phase. The magnitude is more useful to look at. And that's going to be the amplitude of V reflected over the amplitude of the incident. That's going to give us the magnitude. But it is important always to keep track of the phase as well. So there's some instances where it's useful to look at the phase to understand something about the interconnect itself. But it's really critical to keep track of the phase if you want to do any manipulations of the S parameters and convert it to the time domain, or you want to add or subtract or multiply S parameters together. You need to keep in mind that it is a complex number, and you need to keep track of the phase throughout those manipulations. So that was a one-port device. Now we're ready to look at a two-port device here. So we have maybe some trace again here, but now we have, you can see, a second port that we have another port of our network analyzer connected to. Again, that's a 50 ohm port on the analyzer. And now we can send a waveform in from, say, port 1 on the left, and we can measure what gets reflected back, and we can look at the return loss again. And the return loss is going to tell us about any impedance variations in the device. And it's also going to tell us a little bit about the loss in the device in this interconnect. So you can imagine if we send the signal down some really long interconnect, it reflects back. If there's a lot of loss in that interconnect, you're going to see that in the reflection. The amplitude is going to be reduced compared with the reflection that happened earlier in the interconnect. So you might see a term out there sometimes called VSWR, and that's basically another way to talk about return loss. It's less and less common to see this term, but it can be just easily calculated from S11. So we can also now look at the waveform that comes out of the other end, out of port 2 on the interconnect, and we can measure insertion loss. And insertion loss is just the magnitude of our S21 in dB. And this is the transmitted signal coming out of the other side of the interconnect, and this is going to tell us mostly about the loss in the interconnect, but it's also going to provide some information about impedance and reflections, because any energy that's reflected back out of port 1 obviously is not going to come out of port 2, and so we'll see some information about the impedance. And just this is always whenever you look at S parameters, this is always a good sanity check to do, is for a transparent interconnect, we should see S11 should be a very large negative value, so we shouldn't see much energy reflected back. And S21 should be basically 0. So if you have a network analyzer and you connect 2 of the ports together, you should essentially see a transparent interconnect, and you should look to see these 2 things here. So I hinted at some connection between the insertion loss and return loss, where basically if we send in some signal and some is reflected back and some gets transmitted through, there should be some connection between what's reflected and what's transmitted. And so there should be some connection between the insertion loss and the return loss. But the question is, what is that? And this is an important question because most likely what you care about is the waveform that's actually transmitted through. Right? In some kind of system, you're trying to transmit data from one side of this interconnect to the other. So ultimately what you care about is what's getting to the receiver on the end of port 2 here. So it'll be interesting to see how this reflected waveform impacts what's transmitted. So a sort of, I think a logical guess is that the incident is going to be equal to the reflected plus the transmitted, right? If it doesn't get reflected, it's going through the other side. And if you put that in S parameter terms, that would be S11 plus S21 is equal to 1. So that just says what we send in is the sum of what's coming out of both ends. But that's not really true because there's no conservation of voltage. But there is conservation of energy, and the energy in a wave is roughly the square of the voltage. So we can look at basically 1 equals S11 squared plus S21 squared plus any losses in the system. And the losses in the system might be conductor loss, dielectric loss, any crosstalk or coupling, or radiation. But if you assume a lossless interconnect, we have now a solid relationship between the reflected and transmitted signals. So we can see that the insertion loss is equal to the square root of 1 minus the square of the return loss. So to understand what that really means, let's plot that so we can actually see basically how much reflected signal we need to have before we need to worry about it impacting the transmitted signal. So if we plot that equation in the middle here, you see a result which I found pretty astounding the first time I saw this, which this plot is showing on the vertical axis is insertion loss and the horizontal is return loss. And so basically 0 dB return loss over here on the right side is all of the energy, 100% of the energy reflected back. And over on the left side is almost none of the energy reflected back. And then on the vertical axis, we can read off the impact on the insertion loss. So if you look at, for example, minus 20 dB return loss, this means that 10% of the energy is being reflected back out of port 1. And even with 10% of the energy coming back, this has almost no impact on the insertion loss at all. If you look at minus 10 dB, this means that 30% of the energy is reflected back. And you can see only a half a dB impact on the insertion loss. So this is pretty amazing result. So we can take a lot of energy reflected back without much impact on the insertion loss at all. So what does that mean? If you want to make sure that your return loss does not have a significant impact on the insertion loss, well, you want to make sure that your return loss is probably lower than 13 dB. So if you go to like minus 10 dB here, you're going to see a 0.5 dB impact on the insertion loss. So if we take this minus 13 dB, what does that mean for the impedance? So what impedance discontinuity is going to give us this minus 13 dB of return loss? So if we have a 50 ohm transmission line, that's going to be a 12 ohm impedance variation. So if the impedance doesn't vary more than 12 ohms, you're probably not going to see really any impact on the insertion loss. So this was a pretty amazing result when I saw this the first time. But it acts as a good rule of thumb when you're looking at test parameters to understand how much return loss is too much. So there's some different common patterns you'll see in S parameters as you look at these plots. And I'd like to talk about 4 of them here, 4 pretty common patterns you see in S parameters, and talk about where they come from and what it can tell us about our interconnect. So in almost every return loss measurement you see, and sometimes in the insertion loss, you see ripple. So every time you look at S11, you'll almost always see some ripple. So where does that ripple come from? Well, it comes from reflections, but we'll go into more detail in terms of where the shape of that ripple comes from. Insertion loss, typically see a monotonic drop-off. So as you go to higher frequencies, you see more loss. Sometimes you can see broad dips in the insertion loss from quarter wavelength stub resonance. And then sharper dips from coupling to cavity or coupling to floating metal in the circuit. So the first one I'll talk about here is the ripples in S11. So let's look at an interconnect that we'll measure here. And this is, we're going to do connect send some wave through this, but we have a 50 ohm impedance here on one port and a 50 ohm impedance on the other port. But our interconnect here is going to have an impedance that's less than 50 ohms. Let's just call it 30 ohms. So we'll look at a few different cases, but in the first case, we're going to look at when the length of this interconnect is much less than a quarter of the wavelength of the sine wave we're going to send through this. And so this would be a case where the frequency is very low. So we send the wave into the interconnect. It's going from 50 ohm impedance to 30 ohm impedance. So when we get some change in impedance, we see a reflection. So we'll get some of the waveform reflecting. And when it reflects off of there, we'll get a phase change, which is based on this calculation here of the reflection coefficient. You see that you take the second impedance, which is 30 ohms for interconnect, minus the first impedance, which is 50 ohms, divided by the sum. But basically, we're going to get a negative number here, which indicates a half-wave phase shift or 180-degree phase shift on the reflection. So we go from, we get 30 minus 50 gives us a negative, so we get this half wavelength phase shift. But some of the waveform is also going to go through the interconnect and transmit and come out the other side. And remember, the length of this interconnect is much less than a quarter wavelength, so the phase shift we get traveling through the interconnect is basically 0. Now it's going from 30 ohm impedance to a 50 ohm impedance, so we're going to get a reflection again. But this time we have Z2 of 50 ohms, Z1 of 30 ohms, so we're going to get a positive number. So we actually get 0 degree phase shift off of this reflection. And then this signal is going to come back out of the other side. It's going to reflect again. We're going from 30 ohms to 50 ohms. We get a 0 degree phase shift on that reflection. And then it transmits out of the far side again. So if you look at these, if you add up these reflected and incident signals here, we see that this reflection has this half wavelength phase shift. This one has 0 wavelength phase shift. So if we add those together, those are going to give us a minimum for S11, or our reflected signal. So these are out of 180 degrees out of phase. They're going to subtract. We're going to get a minimum over here on our reflected S11. On this side, these are in phase, so they're going to add. We're going to get a max for S21. So if we plot that over here, you can see this is what you'll see on any interconnect you look at, is that at very low frequencies, there is no loss. So S21 is 0 dB, and there's no signal reflected, so S11 is some very large negative value here. So at low frequency, all interconnects are transparent. And I think that's something that we all intuitively know when you think about lower speed signals and circuits. So let's go to, so when the length of the channel is much less than a quarter of the wavelength of the signal, the reflections from the front and back are 180 degrees out of phase, and they're going to subtract, and we'll get a minimum. So there's no net reflection, and all the transmitted phase waves are going to add together, and we're going to get a maximum at the S21. So let's look at another case here where we have the length is equal to a quarter of the wavelength. In this case, we're going to send in the signal. Again, we go from 50 ohms to 30 ohms. We get this 180 degree phase shift on the reflection. Signal gets transmitted through, but this time, as it goes through the interconnect, it's going to have a quarter wavelength phase shift because we have the length at a quarter wavelength. Then we get another reflection. Again, this one has 0 degree phase shift, but we're going to add that 1/4 of the propagation through the interconnect. And then another 1/4 coming back this way, so we have 1/2. We go now from 30 to 50 ohms, we get another reflection. And coming out of this side, finally, we have a total of 3/4 wavelength phase shift. So now if you add these up, we have in phase for the reflected signal here. So we're going to get a maximum for S11 and 180 degrees out of phase for the transmitted signal. And we're going to get a minimum over there. So if I plot that here, you can see our S11 is up at some small negative value here, and we can see our insertion loss dipping down. And if you think about it, this configuration is going to be true every time we have 1/2 times some integer plus 1/4 wavelength. We're going to get a max of S11 and a min of S21. So let's look at the case now where we have the length is equal to 1/2 of the wavelength. So again, we send the signal in, we get this 1/2 wavelength phase shift going through. We also get a 1/2. We have a 0 degree phase shift on the reflection plus the 1/2. And again, another 1/2. So now we get 1/2 and 1 that's out of phase. 1/2 and 1.5. That's in phase. So we get a min for S11, a max for S21. And you can continue on in this pattern for integer multiples of these cases, and you see this ripple. And remember, if the return loss is above minus 10 dB or say minus 13 dB, we're going to see an impact on the insertion loss. So you see the ripple carry over into the S21 here. So some interesting things you can learn by looking at the ripple. If you think about it, the longer the distance between the reflections, so the longer this interconnect is, the shorter the frequency between the high and low is going to be, so the closer these ripples are going to be. So if you have some very long interconnect, you'll see these ripples are really closely packed together, whereas if you're measuring some really short thing, you'll see these are spaced very far apart. And the larger the impedance difference is here, the larger the modulation will be in this ripple waveform. So I'm just going to show some other considerations here. This is showing a TDR response of a connector. So, a typical test configuration, you have some connectors on there, which might be, SMA launches or something. And those usually have some impedance discontinuity at the launch. So we can see that here in the TDR response. And those will affect the ripple in a different way. So we have some different examples on the right-hand side. In yellow, this is a uniform 46 ohm lossless line. So this is basically the kind of simulation I showed on the last slide. If we add some loss, you see what's in pink here. And you can see that the loss is going to attenuate the effects of all those reflections as we go higher in frequency. And then in red, this is when we have connectors on either side. You can see the connectors, the impedance discontinuity looks larger at larger frequencies. And so you can see the effect of S11 rising here as we go up in frequency. So let's look at some measurement examples of this. Here's an example of a microstrip trace that I measured. And what you can see on this is obviously there's quite a bit of ripple on it. And what we learned before is that means that the return loss is probably pretty high. And it's probably above minus 13 dB to be impacting the insertion loss. So let's take a look at S11 in dB and see what that waveform looks like. So if we look at that, you can see right around here, this is 2 gigahertz per division, but right around above 2 gigahertz, 3 gigahertz, you can see our S11 is somewhere in the 10 dB range, and we're starting to see it impact the insertion loss. And this is getting higher as we go up in frequency. So we can read a few things off of this. One is that there's clearly some loss in this transmission line because you can see the amplitude of the modulation decreasing as we go up in frequency. And there's also probably impedance discontinuities that are due to connectors. So some narrow impedance discontinuity because we can see the return loss is getting larger as we go up in frequency. So let's look at S11 displayed in impedance to see if our theory is correct. So when we look at the impedance plot, we can see about a 15 ohm impedance variation at each end of this microstrip line here. So these are the SMA connectors that we're actually hooking up our test port cables to, and these are very capacitive and are causing a lot of reflections. So this was actually a 50 ohm 4-inch microstrip line with some pretty capacitive launches here. So if we were to remove these connectors from the measurement, we should see the ripple and the insertion loss go away, and we should see the return loss go way down. So on the LeCroy Spark network analyzer, we have a tool on there where we can actually de-embed sections of the measurement. And so I'm going to enable that and see what the effect is on the insertion loss and the return loss. So I'm going to de-embed these connectors out from the measurement. And you can see I can do that with this interface here. I can select I want to de-embed from both port 1 and port 2, and I can put in the delay of how much I want to de-embed off of each end. And now if I look at the return loss, you can see it's been pushed down quite a bit. And if I look at the insertion loss, it has this nice flat monotonic drop-off, and there's no ripple in it at all. So this is a typical response of just a transmission line without any impedance discontinuities. So here's a few other examples. This is a 90 ohm 4-inch microstrip trace, so we can see this is not, the ripple here is not due to connectors, it's actually due to the line being at some other impedance. And so this is quite similar to the explanation that I gave at the beginning. So you can see the return loss is actually starting pretty high here and goes across fairly flat. There's some loss, as you can see the amplitude of the modulation decreasing. And then you can see it rising up a little bit more at higher frequencies here. This is a 50 ohm 6-inch microstrip, and this is, you can see some of the effector of the connectors here. If we look at this 1/2-inch microstrip trace, this is pretty interesting to contrast with the 6-inch trace because now you can see how much wider the ripple looks here for this really short trace versus the 6-inch trace where the ripple is narrower in the frequency domain. And this is an example of some very low loss material, short trace. You can see that the return loss stays very low, all the way up to 20 gigahertz here. And the insertion loss, you can almost not even see it. It barely comes off of 0 dB. So this is a very high-speed interconnect. Not going to have much loss, insertion loss or return loss. So the next pattern here is the attenuation and insertion loss. So when we send a signal through an interconnect, what comes out of the other side is, even if there's no reflection, so this is a uniform, perfect 50 ohm transmission line, what comes out of the other side is some attenuated version of the input. And the attenuation drops off exponentially with the distance. So here's an equation that can relate the output voltage to the input voltage, and you can see this exponential relationship here in terms of the amplitude. So if we convert that to S parameters, we can say the S21 is V out over V in, and we can get this equation, which is basically telling us that S21 is giving us the insertion loss, which is essentially just the loss in dB per inch, which we're calling this alpha factor, times the distance of the interconnect. So if the terminations are matched and there's no coupling out of the transmission line, then S21 is just the attenuation. So how much attenuation there is through the interconnect. So this is an estimate of the attenuation per length per inch of a transmission line. And this is given, you have 1 over the width of the line times the square root of the frequency plus, some integer, so 2.3 times the frequency times the dissipation factor times square root of the dielectric constant. So you can use this as an estimate to calculate the loss in dB per inch. If you plug in the numbers here for FR4, a good rule of thumb, and this is not an exact figure, but it's a good rule of thumb to use for FR4 is 0.1 dB per inch per gigahertz. So that's a great number to use if you want to just get a rough estimate of what the loss is going to be in a channel, or you're looking at a measurement, an S parameter file, and you want to just quickly check in your head if it makes sense what you're seeing. You can use this figure of 0.1 dB per inch per gigahertz. So we can check how well this equation up here works. So this is a plot of loss this is based on plotting the equation in black here, and then a couple of measurements of two different transmission lines, giving the attenuation in dB per inch going across the frequency here. So you can see this works pretty well, and it's a good estimate of the loss. So the loss should be, you'll notice, should be fairly linear in dB here. So as you look at the S21 plot in dB, it should be fairly linear. If it's not, you're probably seeing some effects from the return loss or from coupling on or radiation or crosstalk. The next pattern I want to talk about is the quarter wave stub resonance. So this is a routing topology here that you typically want to avoid at higher frequencies because of this quarter wave stub resonance phenomenon. So basically we have a signal that we're transmitting from the left side here to the right side, and there's just a stub in the middle that is open on the end here. So the length of this stub, has some length in inches, but also a time delay associated with it, and we can roughly calculate the time delay by taking the length over the propagation velocity, which we can estimate as 6 inches per nanosecond. But when we send a signal down here, we send some sine wave through our interconnect. When it gets to this stub, how it propagates from there is going to depend on the impedance it sees in both directions. And since the impedance is going to be the same, half the signal is going to go down to the end here and half is going to go down the stub. And when it gets to the end of the stub, it's going to reflect. And this is an open, so it's actually going to see a 0-degree phase shift as it reflects back. Again, it's going to come to this split. Half the signal is going to go back to the transmitter, and half is going to go out to the receiver here. And this reflected signal here is going to combine with our original transmitted signal. And how they combine is going to depend on what this phase shift is here. And that phase shift between these two waveforms is going to be twice the time delay of this stub here. So the time it took for the signal to travel down, reflect off, and come back. So when that value, 2 times the time delay, is equal to half a cycle, then these two things, waves will be 180 degrees out of phase. They're going to subtract from each other, and we'll get a minimum at the receiver here. So if you just divide the 2 over, that says when the time delay of the stub is a quarter of the cycle of the wave, we get our quarter wave stub resonance. And this is going to be a minimum signal received at the end here. So of course we can take the time delay and we can convert that to frequency by taking we can take the wavelength and convert that to the frequency by taking the inverse. So this gives us that the time delay is 1/4 of 1 over the frequency at that resonance. And just flip that around, and we get a rough rule of thumb here by plugging in this 6 inches per nanosecond for the time delay here, length over 6 inches per nanosecond. We can calculate rule of thumb. The resonance frequency is going to be equal to 1.5 over the length in inches is going to give us the resonance frequency in gigahertz. So this is a useful rule of thumb when you're looking at S parameters or when you have a stub that you're thinking about leaving in place to look at if that's going to cause any problems in your design. So let's look at an example here, a simulated example. Again, we have the same topology here, and we look at the S21, the insertion loss. We can see these big dips in the insertion loss, and these again are coming from the quarter wavelength stub resonance. But let's look, basically we can see at 3 gigahertz we have a resonance. So if we use our rule of thumb here, we can calculate the length as 1.5 over 3 gigahertz is going to give us 0.5 inches. So this stub is roughly 0.5 inches long. So when you're looking at something like this, it looks pretty bad, right? The insertion loss plot looks pretty bad, but depending on what sort of signal you're trying to send through here, it might not be a big deal. So if all your signal power is below 1 gigahertz, you're probably okay. But if you want to send through, for example, a 6 gigabit per second signal, well, Nyquist is going to be at 3 gigahertz, and you're probably not going to have any eye opening at the receiver. So the energy reflects actually all back to the transmitter, and so if you look at S11 here, you can see where we have a minimum, and S21 where we have a maximum at S11. So that energy that's not making it to the receiver is reflecting back to the transmitter. So here's a measurement example. This was just a small stub structure I had on a board that I measured. And you can see if you look at the S21 plot, we see that big resonance right here. And the scaling on this is 1 gigahertz per division, so this is roughly here at 3.9 gigahertz. And again, you can see that energy is coming back into S11. But using our rule of thumb, we take that 3.9 gigahertz, and we see that stub is roughly 0.385 inches long. I measured this at 3/8 of an inch, so that's actually pretty close. So it's a pretty useful rule of thumb to use when you want to figure out where these resonances are coming from. Here's another example showing a quarter wavelength stub resonance. And this resonance is from a via stub. And this is showing a comparison of the channel with the via stub in place and with the via stub back drilled to get rid of the stub. And you can see exactly that this via, sure enough, that via is what's causing this big resonance. And if we look at differential S parameters, you can see the resonance is still there in SGD21. So the resonance here, we're calculating it as 7.5 gigahertz, and we can see we measured it around 7 gigahertz, so it's matching up pretty well. But this is kind of a interesting case here, because depending on what frequency you're trying to use this channel for, you may or may not care about this resonance. So, back drilling vias adds, maybe a couple cents on the cost. So that's not something you necessarily want to spend money on if you don't need to. So if your signal power is all below 4 gigahertz in this case, you probably don't want to spend the money to back drill the vias. But if you're trying to send a 14 gigabit per second signal through this channel, well, you definitely want to make sure that you get rid of those stubs. So the fourth pattern I have here is the coupling to high Q resonances. So these are going to be narrow dips in the insertion loss. And high Q resonators are usually any floating metal or I think more typically plane cavities. And the most common place to see it is in vias. So you have some layer transition here. This is an example. We're just transitioning from a trace on the top of the board down to the bottom of the board. And as the signal is going along these traces, it's pretty obvious where the signal return path is. So we have the signal propagating along, and there's a ground plane right underneath it. So all the signal return current is flowing in that ground plane. But when it gets to the via, as the signal travels down the via, there's no obvious signal return path, and it takes some complicated route, and the energy ends up coupling out into the cavity. And there's a simulation here that shows what it looks like to send a step through this via, and what the voltage between these two planes looks like when the signal goes through that via. I can start the simulation here, and you see basically this energy coupling out into the cavity, reflecting off the edges here, and just bouncing around inside of there, which could be causing noise, crosstalk, and just noise on other transmission lines or inside of your circuit board. So this is a measurement example of cavity coupling in a 4-layer board here. So this has a differential pair that comes down here, and it transitions down through some vias and comes back out the other side here. But you can see there's some different measurements on here of the length of the board and the length between different connectors and structures on this board. And we'll see how when the energy couples into the cavity on this via, it bounces around, and you can see the signatures of these different distances in the S parameter. So we can use this equation to give a rough estimate of the resonance, the resonance frequency of the coupling in the cavity. And this is the measurement of S21, which is looking at, this is the differential insertion loss looking from these two connectors over to here. So we're sending the signal through these vias. And if you look at the length of 3.25 inches, which is the width of this board here, and you plug that into our equation here, you can see that we expect to see a resonance at 0.92 gigahertz. And sure enough, if you look on the S21 plot, you can see a little resonance right here. We also have this 1.187 inches, which is in between the SMA launches here. And that would give us a resonance of 2.5 gigahertz, according to our equation. And sure enough, you look on the S21 plot, you see a nice dip right here at 2.5 gigahertz. And 0.8 inches in between the connectors here. We can see 3.75 gigahertz. And you see that here, and this one is a little wider because this is almost 0.8 inches as well. So you can kind of see both of those distances in that one dip. So the solution here is to add some signal return path for the signal on this transition. So you can add some signal return vias around the signal vias there, and that would help to reduce a lot of this bouncing around of the energy in there. So that covers the 4 different S parameter patterns I wanted to today, and as well as the relationship between insertion loss and return loss. So hopefully that should help you guys get some insights out of your S parameters. I know looking at S parameters, if you don't have a lot of experience with them, can not be the most intuitive experience. So it's good to have some rules of thumbs and some patterns to look for in them that can help you gain some insights into your interconnect and connect real-world features in the interconnect with things that you see in the S parameters themselves. So at LeCroy, we sell a network analyzer called the Spark. And this will measure S parameters up to 40 gigahertz. And a lot of the examples I showed in the presentation today were measured on the Spark. So this will help you get those S parameters that then you can use some of the techniques I talked about today to get some insights on your interconnects. So the Spark has some pretty nice features. It has a single button press operation, built-in automatic calibration. So all you need to do is hook up your device and press go, and you'll get the S parameters that you need. And it's a fairly low-cost, high-performance instrument. So let us know if you'd like to get more information on the Spark. But thank you guys for attending, and I'll open it up for any questions.
Okay. Thanks, Stephen. Thank you to all of our attendees. We do have a couple questions. The most popular question is, will these slides be available for download? And the answer is yes. The slides will be available to download, and I will also be sending out an email that has a link to the recorded presentation if you'd like to refer to this presentation again or share it with some colleagues. Back on, I believe, slide 7, Archie had asked, how do you measure the amplitude of the incident and reflected waves since they are on the same port? It's like either 6 or 7.
Yeah, so this is kind of it. So there's some different techniques that can be used in a frequency domain instrument. You use a directional coupler. So a directional coupler will pick off the signal only in one direction. So we have some calibrated signal we send out, which is this incident signal. And typically there's a calibration process that's done. So this signal is really well defined, the incident signal. And then a directional coupler can be used to pick off only the signal coming on the return. For a time domain based instrument, you send in a fast edge, and you have a sampler that samples that incident fast edge, but then it also looks for any reflections coming back. So it can see the reflections coming back because it happens later on in time. So the time domain instrument separates them by time, and the frequency domain instruments use a directional coupler in order to pick off that reflected signal.
Okay, so Ralph just inquired, and I believe it's about the same topic. Can this be used over longer distances, say a meter or so, and be of use, or even longer distances?
Yeah, so a meter is no problem for almost any network analyzer type of instrument out there, or TDR. And probably, up to maybe, I think the Spark will work pretty well up to about 15 or 20 meters, actually. It also depends on the loss, how much loss. If it's a really lossy interconnect that's 20 meters long, you're going to be in trouble. There's also specially designed instruments out there for measuring really long things, like there are like cable testers and things like that that are meant for measuring things which might be 1,000 meters long, for example. Back in my old job, we used to get a lot of questions. One of the favorite applications for this cable tester was measuring cell phone antennas and looking for, apparently, people like to shoot at cell phone antennas out in the desert, and they used their TDR to look for where the bullet hole was in the antenna cable. And so you could measure things, these cables might be 1,000 meters long.
So Ralph, hopefully that answers your question. If not, please ping us back. Same goes for you, Archie. So we have one gentleman says that he came in late. Does this equipment also provide TDR results?
Yeah, so on the Spark, we can measure S parameters and show kind of all the things I talked about today. But there's also a live TDR mode, which will show just the live TDR waveforms and TDT waveforms. And that's really nice for some debug capabilities because you can see the results changing live on the display. For example, if you want to twist around a cable or jiggle a connector, you're able to see if that has a big impact on the TDR results.
Okay. All right, so CJ, hopefully that helps. If not, let me know. And Norman asked if there's audio going to be included. So there will be 2 things sent to you later, a link to the on-demand presentation, which is this actual presentation recorded with audio, and then a copy of the slides in case you want to take notes. Greg asked, I think while you were back on this last on slide 7, what is the relationship between Nyquist frequency and data rate?
So yeah, if you have some non-return 0 signal, so that has some bit rate, so that's sort of the standard communication that's used today for things like USB, PCI Express, Ethernet, things like that. The bit rate is going to be double the Nyquist frequency, so the underlying clock rate is going to be half of the bit rate. So if you have a 5 gigabit per second USB 3 signal, Nyquist is 2.5 gigahertz. And there's like a rule of thumb we use in the oscilloscope industry for making recommendations on how much bandwidth you need. Typically, you want to make sure you're capturing at least the fifth harmonic, and so you can kind of use that same rule of thumb when you're looking at S parameters and figuring out how much bandwidth you need in the channel. Most of the spectral content of the signal that is most important is contained in the first up to the fifth harmonic. So if you have, again, a 5 gigabit per second signal, Nyquist is 2.5 gigahertz, so you would take 5 times that, or 12.5 gigahertz. But if you have a lot of loss or problems right at Nyquist, that's where the majority of the spectral power of the signal is. That's going to cause some big problems in the link.
Okay, so that was Greg. So Greg, hopefully that answers your question. If not, please ping me back. Just so that everybody is aware, I will also include Stephen's email information in the follow-up email. So should you think of anything else, you're welcome to call him. We also have technical support available Monday through Friday, 8 to 8. And I'm always here. Couple other questions, so thank you for everyone for still sending them in. Sebastian asks, do I translate from the time domain into the frequency domain by a simple FFT or vice versa with an IFFT, or is there a counterintuitive caveat to it?
Yeah, it's pretty much as simple as that, using an FFT or an IFFT. And when you do that, you need to make sure it's a complex FFT that you're doing, because there is the phase and the magnitude information in there. But if you use you can download the software for the Spark from our LeCroy website, and you can download that for free. And that'll allow you to import S parameters into the Spark, and you can transform between time domain and frequency domain. You can show impedance, step response, or magnitude and phase of S parameters. So usually it's easier to find some software like the Spark software out there that'll do a lot of those transformations for you. But all the information is there in either domain. It's just a matter of converting back and forth to learn different things about the interconnect.
Okay, so somebody asked a question. All right, so Sebastian, hopefully that helps. If not, I know you know how to get us. Nick, thank you for joining us. Yoon would like to know, what is the OSLT calibration?
Oh, so sort of the first slide I talked about was sending in some signals into the device under test here, so into the interconnect. So we're trying to characterize the interconnect by using some precision signals, right? So we send in these precision reference signals, and we look at how they scatter off of the device. So they're not really precision signals, because we design them as well as we can in the test equipment, but it's sort of impossible and would be really expensive to try to design a really perfect signal to output into the device. So a much easier way to do it, and cheaper, and works a lot better overall, is to do a calibration. So you have some devices that you have these different structures that you measure, which the behavior of them is known ahead of time. And by measuring those, we can create some compensation coefficients, basically, to correct for any imperfections in the reference signals. So there's a few different ways to do it. One of them is this short, open, load, and through. So those are 4 different things that are measured. You measure a short, an open, a 50 ohm load, and a through path. And those are all pre-characterized, and the behavior of them is known. And so we use those to map out this calibration space, so that now we have these precision signals, because we know exactly what they look like based on measuring these calibration standards. So in typical VNA and TDR, you need to hook those up manually to the test port cables and measure each of them. On the Spark, all that is done automatically for you. You just need to press the button and make the measurement. You don't need to hook those up externally.
Okay, you can hopefully this answers. If not, you know how to you can resend in your question. So a couple more. Stephen, do you have time to stay?
Yeah, sure.
Okay, great. Okay, so Norman, you mentioned moving cables may impact results. Is this only due to connector mismatch changing?
Yeah, so when I just answered one of the questions, moving some cables may affect the results. So, if you bend a cable, for example, depending on the quality of the cable and the type of cable, the phase of it might change, and so that can affect the results. It just depends on what you're using. So that's also, it's not necessarily the impedance that's changing. It might be the phase delay. If you kind of kink it all the way, you might get an impedance discontinuity in there. And in connectors and things, just depending on how the connectors are actually mating up, the surfaces are touching. By jiggling a connector, you might see that occasionally it doesn't make good contact, and you get some impedance variation there. So it can either be a change in the impedance or a change in the phase. Typically, the loss shouldn't really change that much.
Okay, so Norman, let me know if that helps. Another question from Sammy just came in. Great, Norm, thank you. How do you characterize back-to-back test fixture? The reason you do this is to measure the S parameter of the fixture for de-embedding. I'm not sure.
Oh, yeah. So there's something I didn't really get into in this presentation, which is how do you actually connect the Spark or whatever VNA you're using up to the thing that you want to measure. And that's a whole other topic that you could spend a long time talking about. But one way to do it is with fixtures. So you have coaxial connectors on the test port cables on the instrument, and we can create a fixture that has coaxial connectors that mate with the instrument on one side and some sort of connector that mates with your interconnect that you ultimately want to measure on the other side. So there's a number of ways that you can characterize the fixtures to try to remove them from the measurement. So one of the ways is to kind of plug two of the fixtures together and measure the whole thing and try to chop it in half. You can also build calibration kits that work with the fixture that you can calibrate out the fixture. The easiest way to do it, and it's pretty accurate, is using the technique that I showed in the presentation here, where we had these big connectors here, and then I de-embedded them from the measurement here. And all I had to do in this instance, this is a unique feature that we have on the LeCroy Spark, is enable this impedance peeling algorithm we use and just put in the delay. And the connectors are de-embedded automatically. So you can use the same technique for fixtures as well. So this makes it really easy, almost trivial, to do that de-embedding rather than having to try to design a special cal kit or do manipulations of different S parameters. You just punch in the values and press recalculate, and as you can see, it works pretty well here. So that's typically what I recommend for people who have the Spark. Otherwise, there's a lot of information out there about de-embedding fixtures and different ways to do that. So
I offered Sammy possible lunch and learn, and come on site and show them specifically with their device. And we also, I believe, have some other presentations and white papers, so I'll take a look and send them off to Sammy. We had a question just come in regarding that. Someone would like to know, what is de-embedding?
So de-embedding is taking an S parameter, and so an S parameter, again, is something that characterizes the behavior of a linear passive interconnect. And it tells us everything we need to know about how that interconnect reacts with signals we send through it. So once we have that S parameter, we can use that to de-embed pieces of the measurement. So basically, we had those connectors in the measurement, but we can take S parameters for those connectors, and we can use that to remove them from the measurement. So de-embedding is removing some piece of the measurement. So for example, we had measured this 4-inch microstrip trace plus these SMA launches here. But if we don't want those in the measurement, we just want to measure this microstrip trace, we can de-embed them or remove them from the measurement, and we can see how things change. So de-embedding is removing a piece of the measurement.
So Patrick, hopefully that helps. Again, I do believe we have app notes and on-demand webinars regarding that, so I'll look them up and send them to you. Sammy's good. Anyone else have any questions? I think I've read them all. And again, I really do want to thank everyone for joining us. The questions are great, and Stephen is available to answer additional questions if you think of them. And I think that's it. I think that's it for today. Next month we'll have one on essential principles of jitter, so look out for your email invites. And I wish you guys all a happy day. Thanks, Stephen.
Thank you, guys. Bye.